the angular speed changes. So I'm left with negative g sine theta is equal to r alpha. Now it's still not quite in this form yet. Let's manipulate this form just a little bit and then we'll go back over there. Newton's, if this is all I have acting on an object, then if that's the total force, this is equal to mass times acceleration. So I have a relationship here where I've got a negative on, or with opposite signs here. And I have something about where it is relative to the acceleration. Well, theta is basically telling me where it is in terms of how far I pull it back, but this pesky sign here keeps us from putting it into that form. So we flash back to the days before computers, when it was all done by hand. And we talk about the small angle approximation. If theta is small. When you got the two less than signs, this means much less than. If you need a number, if it's 10% or less of whatever you have on the right-hand side. So if the angle is small, now notice I don't have any units over here, so what are the implied units for the angle? Yes? So 1 radian is 50-something degrees. I want to say 52. It's either 52, around 52 or 57, I think. Somebody do the quick conversion here. 1 radian equals how many degrees? (180 divided by pi), if you want that route.
57.3.
57.3? Okay. So if it's much less than 57.3 degrees, it turns out that the sine of theta is approximately equal to theta. Now, I'm hoping that you can see the difference in colors. I guess Bayan and Jahir, you two are the farthest away. Can you see the colors? This is a plot of a function equal to theta, sine theta, and tangent of theta. The one in red, the one in the middle, is just theta. That's just a straight line. Sine of theta is the green one, and that's the one that veers down, and then tangent of theta is the one that goes up. So using the small angle approximation, notice that there's a huge overlap in the 3 graphs for small angles. As a matter of fact, let's see, that's for tangent. Sine's the one I care about right now. I have it for cosine, I don't have it for sine. Oh, there we go. That we are 10% off when theta is 0.767. We are 5% off at 0.545 radians. So about 31 degrees, we're 5% off between sine of theta and theta, when theta's in radians. So this function right here, or this equation right here, if the angle is small, becomes negative g theta is equal to r alpha. I now have a relationship relating position and acceleration. It just, in this particular case, it happens to be angular. Flash over here. I have this direct parallel here. K directly relates to G, M relates to the radius of the pendulum. And so now I'm just going to call the length of the pendulum L instead of R, to put it in more traditional form. And with this parallel, we have something that approximates simple harmonic motion, and therefore these hold true. And so for a simple pendulum, the period is 2 pi times the square root of, well, M in that equation is L in that equation. K in this equation relates to the coefficient of theta, which is G. So we have the formula for the period of simple pendulum. Let's find out how accurate it is.
T is tension?
Pardon?
T is period.
T is period, yeah.
Okay.
This is the reason, one of the reasons why I don't use T for tension earlier. I use F sub T. Loop in it. That is horrible. Now the mass doesn't matter. Where it does matter is our approximation for the simple pendulum is that we have a point mass. So whatever mass I pick, it needs to be small compared to the length of the string. So if I got a really big mass, then it would become a little bit more off. But hopefully this is small enough here. All right, let that unwind a little bit. So let's make our predictions of what the period should be. L is the distance from the pivot point to the mass there. So if I pull it like that, the pivot point is basically the center of this rod.
Is it to where it attaches or the center of the mass?
It should go to where the center of mass is, down there, and then the pivot point up here. I think that's roughly the middle of the pendulum. So I'm getting 64.5 centimeters. So I have L, 64.5 centimeters, or 0.645 meters. G, we know, is 9.798 meters per second squared. So what is the predicted period?
1.61?
1.61. Everybody else got the same thing?
Yeah.
Units?
Seconds.
All right. So what we're gonna do is we're gonna time, so I need people who have access to a stopwatch on their presumably phone. And we're gonna time how long it takes to do 10 oscillations, and then we'll just divide by 10. So if there's any credibility to what we're talking about, it should take about 16 to 17 seconds of recording. Now, part of this is that I need to make sure that the angle is small, so I'm not gonna pull it back too far. All right, so who's gonna be doing timing here?
So what we just figured, that's theoretical, right?
It's all on you. All right. Pardon?
I said that was theoretical?
Yeah, that's our theoretical.
Will you tell me when we go?
Yeah, I'll do
Okay.
3, 2, 1, go. When I say go, I'm gonna release.
Got it.
And then I'll count. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. What'd you get?
15.7 seconds.
So you had 15.7
Yes.
for 10 oscillations, so that gives us 1.57 seconds. So that was our experimental, that's sort of theoretical. So 400, so about 3% off. We don't have too many experiments or demonstrations where we're that close.
And that was the, okay.
You look like you're about to follow up.
The period, the blue one is the one that we predicted,
Correct.
and then the one underneath it is the actual.
As much as we can trust Sarah's reflexes. All right, any questions up to here?
I don't believe so.
All right, just going back to normal simple harmonic motion. I've got a spring here that hangs, we'll just say 50 centimeters, 0.5 meters. I attach a mass to it, and it hangs in equilibrium, so these are equilibrium. Let's say it's now 0.8 meters, and we'll put a 3 kilogram mass. And then I pull it down, still 3 kilogram mass, I pull it down an additional, what have I not used yet, 40 centimeters. How fast is that mass going when it passes this point right here? So the first two scenarios are equilibrium, the third scenario is not. Yes, Olivia.
Is this an ideal spring or does it have that?
The ideal spring. Not that marker. All right, so given a situation like this, the big purpose of the first bit is to figure out what the spring constant is. We have to know how stiff the spring is in order to figure out how fast the thing's going to be snapping back. Since this is an equilibrium force diagram, what are the forces acting on the 3 kilogram mass in scenario 2 here?
The spring is.
All right. What's the acceleration of it?
0,
I hope so. Why?
because it's in equilibrium.
Yes. So I know acceleration is 0. So whether we choose up positive or down positive, it really doesn't matter. Let's just choose down as positive. Why not? So I have W minus the spring force is equal to 0. For those who desperately wanted mass times 0, which is 0. There's the equation substitution. We have a formula for W. What is it?
mg.
Do we have a formula for the spring force?
Negative K change in displacement.
Yeah. Just displacement. Change in position.
Change in position.
The negative is a directional thing, and I've already taken direction into account, so I'm not going to put an extra negative in here. So it's just our spring constant times how much it displaced is equal to 0. So I'm trying to solve for K, so K is going to be equal to mg over delta x. So we can just do a little plug and chug. Let's just make life slightly simpler, and we are on some magical planet where g is equal to 10 meters per second squared. So I have 3 times 10 divided by, what is my displacement here?
0.3 meters, centimeters.
Yeah,
meters.
0.3 meters.
Meters.
This 3 right here is kilograms, and this is meters per second squared. And what we end up with here is 100 newtons per meter. So I now have some idea how stiff it is. In order to stretch the spring a meter, it takes 100 newtons of force. To give some context, my weight is about 1,000 newtons. So if I if I hung on the end of that spring, I could stretch that thing about 10 meters. All right, well, we still haven't gotten to what the value of how fast it's going. I pull it down 40 centimeters and I let go. Let's see, I know the mass and I know K. So let's do the formula point of view, what we had done last time. Omega is the square root of K over M, which is the square root of 100 newtons per meter, divided by 3 kilograms. Let me just say an answer.
I got 5.77 meters per second.
Oh, maybe we
Radians per second?
Radians per second. Yeah, it's angular frequency. I know my position graph, or my position is some amplitude times the cosine of omega t plus phi. What's my amplitude?
.3 meters.
So we're talking about after I stretch it. Not when it's in equilibrium. If it's in equilibrium and I just have it sitting there, there are two separate conditions, then my x of t is some constant.
And is that 40 centimeters, like the whole thing, or the additional?
It's just 40 centimeters from its equilibrium
Okay.
position.
So it'd be 0.04 meters, would be the amplitude?
Too far.
0.4.
0.4.
0.4.
All right, so this is equal to 0.4 meters times the cosine of 5.77 radians per second times time. What's my phase shift?
Zero?
Yes. Because I'm starting at the maximum value. I now have a function here which is going to describe how fast it's moving up and down. Or sorry, we'll describe where it is at some particular time. I know that my velocity time graph, or my velocity function with respect to time, is negative a omega sine omega t. I know phi is 0 now. I'll still stick phi in there, but it's going to be 0. So I have negative 0.4 times 5.77